Welcome to the 23rd episode on my channel. In the previous episode, we learned how the difference in the redox potential of the oxidation reactions within the aqueous system controlled the separation of manganese from iron as oxides and hydroxides. With the result, manganese remained dissolved in the seawater while the iron precipitated. Thus, one says manganese has a comparatively longer residence time than iron. We have learnt in an earlier episode that both iron and manganese form soluble cations in seawater or in the oceans because of their low ionic potential, that is Z by R. For Fe plus 2, it is 2.7, and for Mn plus 2, it is 2.5. They both are therefore leached away almost simultaneously from their host rocks, constituting the continental crust. We mean the Tonian continental crust, isn't it? However, the continuous and prolonged oxidation of Fe plus 2 to Fe plus 3 required 0.77 volts, and later of Mn plus 2 to Mn plus 4 required 1.51 volts, which preceded the amazing sequential precipitation process, forming extensive sedimentary deposits that also required a tectonic stability, isn't it? Since for achieving their oxidized form, Fe plus 3, the ionic potential increases to 4.7, and for Mn plus 2 to Mn plus 4, it becomes 6.7. They precipitate as hydrolysates, therefore. All these processes, say leaching, dissolution, transport, oxidation, and precipitation, to act continuously for a geological time period of a few million years, couldn't have been achieved without a tectonic stability, isn't it? Tectonic stable conditions, both in the provenance as well as in the basin of deposition. You know that the two iron group elements, namely nickel and cobalt, which are commonly associated with iron, say with massive magmatic intrusions in endogenic processes. Cobalt needing a much higher redox potential or oxidizing potential in aqueous systems than that required for oxidizing iron and manganese, therefore does not precipitate. While nickel has no oxidized form like Fe and Mn, so it also doesn't precipitate. They both have a longer residence time, therefore, and remain dissolved in the aqueous system of the oceans. There are many other valuable elements, though, like the rare earths or the lanthanides, uranium and thorium, which precipitate as hydrolysates in specific conditions and form economically viable sedimentary deposits. Besides, the iron and manganese hydroxide minerals also possess very strong adsorptive power, similar to the clay minerals. They absorb many elements like the Re, tungsten, vanadium, arsenic, antimony, nickel and cobalt, molybdenum, lead and zinc, while they precipitate. It is more distinctly accomplished, especially in the weathering profiles, like in gosans and in regolith. Sometimes the adsorbed elements occur in such amounts, say exceeding their average presence in rocks, that they can be recovered or retrieved as important byproducts during the beneficiation process. We know that highly charged cations get more readily adsorbed than ions with lower charge. I guess you are familiar about the world's most important rare earth deposits occurring in South China. These deposits are described and classified as the regolith-hosted deposits. And such deposits are being explored at present globally because of the critical industrial usage of the REE. Of course, we will describe and discuss about the economically viable deposits of REE in future episodes. However, the most significant association in the present discussion on precipitation of FeMn deposits is of silicon, Si4, which precipitates as cryptocrystalline silica, as chert, and as jasper. This kind of silica is associated intimately, intertonging, and alternating with the microlayered FeMn oxides and extend undisturbed over large regions covering the entire basin of deposition. That kind of microlayering of iron manganese hydroxides and association of silica is mostly accomplished perhaps through the mediation by cyanobacteria or by blue-green algae within the zone of photosynthesis. The cryptocrystalline silica, like the jasper, often contains tiny iron particles, and the FeMn oxidates are thus regarded also as biochemical precipitates, about which we will be discussing in the next episode. We have also learned in a previous episode that these precipitates have been shown in groups that have common fences of EHPH during precipitation. It is depicted by Krumbine and Gravels in 1952. For Fe, Mn, and Si, the fence happens to be common between 7 and 8 for precipitation, and the process is accomplished in the shallow oxidation zones of oceans, say above the thermocline. The fence proposed by R.M. Garrels in 1960 for the dissociation of water, H2O, into oxygen and hydrogen represents EH is equal to 0, indicating the boundary below which the ocean environment is oxygen poor. This fence is shown to be sloping towards the increasing pH regions, that is, towards increasing alkalinity. It also coincides approximately with the FeMn oxide carbonate fence. What does that imply? It implies that the increasing pH or the alkalinity helps the oxidation process in the ocean system. Conversely, the decreasing pH promotes the stability of the dissolved elements in the aqueous system. You will agree that the continuous precipitation forming the extensive FeMn-Si deposits should be extremely sensitive to the EHPH environment of the medium. Maintaining such a fence for a geological time period does require a tectonic stability, isn't it? Let's see how the oxidation took place. We know that the surface interaction with the atmospheric oxygen and carbon dioxide is possibly the only thing possible in the shallow regions of the oceans, where the milieu also remains chiefly alkaline due to dissolved elements. With depth, it gradually becomes oxygen poor with lower pH. Applying the Tectonian principle once again, it could be visualized that such a variation was also in the Neo-Proterozoic oceans about 700 to 750 million years ago. In the supergene processes also within the continental crust, the parting of Fe and Mn and the association of cryptocrystalline silica gets even more distinct, say in the region above the water table. We know that the environment there also becomes gradually less oxidizing as well as less acidic. This is regarded as the zone of supergene oxide enrichment. You will also realize that this interaction of the cryogenian atmosphere with the Tonian crust, Tonian continental crust, was very crucial. Since the Tonian crust consisted of both felsic and mafic intrusions, the interaction should have released and dissolved elements like sodium, potassium, calcium, magnesium, iron and manganese, adding to the salinity and alkalinity of the opening cryogenian oceans. We have also learned that some deformed and metamorphosed slabs and rafts of the Tonian crust also descended to the oceans as the cryogenian glacial debris. For such oxidizing reactions to proceed continuously in the ocean system and to precipitate extensive blanket deposits of Fe, Mn and Si, representing a geological time period of a few million years, required tectonic stability, of course. The tectonic stability in the basin of deposition was a prerequisite for these geochemical reactions to happen. We will look into the possible mediation by the cyanobacteria also in this process of precipitation in the next episode. Thank you.